Hi Yagna, hi Drishti, are you guys able to hear me? Hello. Okay, that's great. Can you just try speaking once so that we know that the recording is going fine? So we would be starting in a few minutes. We would wait for people to join, and once people are here, we would be joining with the session. Hi, so we would be starting with the session now. I am Raghubir Prasad, guys. I would be trying to cover all the portions for Midsem for thermodynamics, and we would basically be covering module 1 and module 2 in depth, and module 3, if we get time, we'll cover. So I'll try and share my screen. Just let me know if it is visible to you guys, okay? Hi, are you able to see my screen? Just react with a thumbs up or anything. Okay, that's great. So firstly, we would be starting with what exactly is thermodynamics. So as I have mentioned over here, it is the study of energy transformations. Okay, how energy transforms from one form to another, and how these energies interact with each other. Like, no, how if I have a hot coffee mug, how it interacts with the surroundings, as in the how coffee vaporizes with time and how steam is being generated. All that we would be learning in this course. So here we have a basic definition. The universe that we take in consideration when we study thermodynamics is actually a combination of system and surroundings. So what exactly is system? System is nothing but like the specific area or region we choose for studying. So if we are recording the values like the temperature values, pressure values of a particular area, that part is our system, and everything apart from the system is the surroundings. That's why these two complete and make the universe. Now boundary is what separates the system and the surrounding. It separates the system and surrounding. So we have a system, then we would have a boundary, and up outside the boundary whatever is there, that's the surrounding. So that's the basic definition. And how does the interaction take place? Interaction can happen in basically two ways. One is by changing of mass, and the other one is by transfer of energy. So on this basis we have classified systems into basically three types. So these are the three types. So anyone, if you want to answer in closed system, what is there? Anybody? Like, I'm basically wanting to know about the energy interactions or mass interactions. What is allowed and what is not allowed. Okay, so let's start. So mass is constant, so which means mass doesn't change. But in a closed system, energy interaction is allowed. Energy changes. And how does energy change? Basically, it happens by heat and work. So these are the two ways in which energy can transfer. So energy changes are allowed. Now in open system, both mass and energy can change. So mass can change and energy also changes. Now the last one, isolated one, neither mass nor energy will change. So mass constant and no energy change. So that's the basic definition of your three kinds of system. And also one important thing in questions, maybe it's not mentioned as a closed system, but they may also write as control mass. That's another way of saying that our system is controlled. Why control mass? Because we see here mass is being constant, so that's why it is called control mass. And this one is called control volume, because when we are not able to define a system wherein mass is constant, we generally define a region, and in that region mass can change but the volume will remain same. That's why this one is called the control volume system. Now each system has its own set of properties, okay, and these are basically thermodynamic properties. So they define the state of the thermodynamic system that we are studying. So we need state to do like the questions that we have in our paper. So we first need to define the state. And what do we need to define the state of the system? These are basically the properties or the characteristics. So we have basically two types of characteristics. One is intensive and one is extensive. Intensive characteristics are the ones which depend on the amount of amount or mass of the system that we have. So and extensives, they don't depend on amount or mass. So for example, let's take a simple example, like we have a sheet of paper, let's say a sheet of black paper. So whether I have a small sheet of black paper or a chart paper which is black in color, the color is not changing, right? If I cut the chart paper into smaller pieces, each piece will remain black itself. But the area of the paper which I have, that is changing. So if let's say I have an origami paper, that will be smaller in size. If I have a chart paper, that is very large in size. But color is same in both the cases. So what we can say is that color is an intensive property, whereas the area is an extensive property. So for thermodynamic properties, the intensive properties which we have are basically temperature, pressure, then these are two which are not very important: refractive index and viscosity. These are not particularly important as per your midsems, but
Excuse me.
if they ask for examples of like intensive properties, you can give. And for the extensive properties which we have is, one is mass, because see, the amount of substance we have, the mass will change, right? Then we have volume. After that, internal energy. Enthalpy and entropy. Enthalpy and entropy will be covering in module 2. You don't need to worry about it right now. So now what exactly are specific properties? So let's say I have any one of these extensive properties, for example volume, internal energy, enthalpy or entropy. When we are doing questions, what we need to find out is, we don't want to take mass into consideration. Like I want to study my system irrespective of its mass or the quantity which I have. So for that we have a thing called specific properties. So if I have an extensive property, I do some operation, it will become intensive. And what exactly is this operation? This is dividing it by mass. So let's say any property, any extensive property divided by its mass. Extensive property when divided by mass. So let's say I have volume. Volume is an extensive property, but when I write small v, one more very important thing, whenever we write extensive properties, these are being represented by capital letters. So capital V is for volume, capital U is for internal energy. For enthalpy we have capital H, and for entropy we have capital S. But when we write specific volume, we write small v. So that small v would be equal to your capital V divided by the mass. Similarly, enthalpy, so specific enthalpy, that is small h, will be the enthalpy divided by the mass. Similarly, entropy will be the actual entropy divided by the mass. Same you can write for internal energy as well. Small u is equal to capital U divided by m. And when you actually open your data book for the questions that you have on module 2, so when you open the data book, you will actually find that the properties mentioned over there are specific properties. So actually you can't make a data book for each and every internal energy. Maybe you have some quantity and I have some other quantity. So both of us are having different quantities. So it is a better way that we take into consideration specific properties when we are taking like extensive properties, which all are there. We usually use specific specific volume, specific enthalpy, specific entropy, or specific internal energy. Now one very small thing, like what is thermodynamic property and what is not a thermodynamic property. So initially, like I mentioned, color is not a thermodynamic property, because the state of my system which I have into consideration, that will not change depending on whether my system is blue in color or black in color. That will not change the state of my system. But on the other hand, temperature, pressure, volume, enthalpy, entropy, all these properties will actually affect the state of my thermodynamic system, which is why these are thermodynamic properties. Now what is the state of a thermodynamic system? So thermodynamic state is basically a condition of a system at a specific amount of time. So like at a given time, what is the temperature of my system, what is the volume of my system, and various other compositions, that will give me the state of my system. And then we have a state postulate. This is very important, guys. So that the state of a simple compressible system can be defined by giving two independent and intensive properties. Independent and intensive properties. So that's why we studied this specific properties over here, because any extensive property which we have, volume or enthalpy, we can just take the specific volume or specific enthalpy, and then I'll get intensive properties, which I can use in my state postulate. Now we would like go through the different types of equilibrium that are there. So thermal equilibrium, very easy. Like if temperature is same, temp is same of like two bodies, or no difference in temperature, which implies delta T is equal to 0. If this is there, we say that the system is in thermal equilibrium. So, and one important thing, whenever two objects are in contact, so let's say if I am touching my laptop, so after a certain period of time, laptop and I will have thermal equilibrium, as in my temperature and the temperature of laptop would attain thermal equilibrium after a certain period of time. So similarly, we have mechanical equilibrium. Any guesses for mechanical equilibrium?
When the net force and net torque on an object is zero.
So no net force. And when I say no net force, there can be individual forces acting on the system, but when we take the vector summation of all the forces, they will sum up to 0. So that's what we mean by no unbalanced forces or no net force. And similarly, no pressure gradient as well. No pressure gradient. So that will constitute for mechanical equilibrium. Then we have phase equilibrium. So phases, what are phases? Phases are nothing but solid, liquid or gas. And don't try and confuse the phase with the state. State is a very specifically defined thing, wherein like we would have some properties, usually two independent and intensive properties. So that will give me the state. But phase is a very loose way of saying. Like if I say ice, ice is solid, so solid is the phase. But when I'm actually giving the temperature, pressure or volume, that's when I'm defining the phase of that system that we have. So phase equilibrium means that there is no phase change, no net phase change. And lastly, chemical equilibrium, like you have almost there is similar, so no chemical change, no net chemical reaction. And when I say no net chemical reaction, I could have two independent chemical reactions going on at one point of time, but their sum would be 0. So like if I have water converting into water vapor and then water vapor is converting back into water, that would be phase equilibrium. But let's say if I have a reaction going on, like oxygen is splitting into two oxygen atoms, and then those two oxygen atoms combine again to give me oxygen, O2, then that would be chemical reaction. But the rate at which the forward reaction is going, that should be same as the backward reaction. So which means rate of forward reaction is the same as rate of backward reaction. And when I have all these four, like when I have thermal equilibrium, when I have mechanical equilibrium, when I have phase equilibrium, and when I have chemical equilibrium, that's when I can say that the system that I have is in thermodynamic equilibrium. So for thermodynamic equilibrium to be true, all these four conditions should be satisfied. Now next we have path. So what? And one more, quasi-equilibrium process. You should just know the definition of that. So what is a quasi-equilibrium process? In which a system is changing its state, but the state change is so slow that each of the individual states that we occur in between the state change, these are also considered in equilibrium. So by nature, quasi-static processes are extremely slow because we want to maintain equilibrium at each individual state as well. Now we are moving on to path. So path is like the sequence of intermediate states that a system passes when moving from one equilibrium state to another. So let me write it down for you. Sequence of intermediate states when moving from one equilibrium state, which is a very important point. So we should be going from one equilibrium state to another equilibrium state, but it is not necessary that the states which we encounter, like let's say this P1 V1, this is my equilibrium state, this P2 V2 also is my equilibrium state, but if I take any random state at here, this should even if it is not in equilibrium, it's fine, it is a normal thermodynamic path. But when these individual states at each point, they are also in equilibrium, that's when we say that it is a quasi-static process. So this blue line actually defines my path over here. This is the thermodynamic path, and then we have a thermodynamic process. So in path, what we are focusing on is the state, like the sequence of states. In this, the manner it will changes between two equilibrium states, and we are more concerned about the properties in a process. So what is happening to my pressure, what is happening to my volume, what is happening to my temperature. That's what I am concerned about when I am considering the process. So the manner in which a system changes from one equilibrium between two equilibrium states. So this is very important over here also. Whenever we are taking change of state, we should be going from one equilibrium state to another equilibrium state. Okay, so again we have four types of processes. One is isothermal, which is again very easy to say, like temperature is same. Then we have adiabatic. Adiabatic we define as Q is equal to 0. And what is Q over here? Heat. So we have no heat transfer. Then we have isobaric, which means pressure is constant, so no change in pressure. And then we have isochoric, which means volume is constant, no change in volume. Got it? So now, okay, first these two graphs. I have a PV graph over here, which means on the y-axis I have pressure, and on the x-axis I have specific volume, not the volume but the specific volume, like I mentioned earlier about the specific properties. So can anybody like to guess like what's the first graph representing? This one, this vertical line. Yagna, Ekansh, Tanishk, Vikas, Sam, anybody? Okay, so let's look at this. So in this, on the x-axis we have volume, and this specific volume is not changing. And when we had specific volume is not changing, what was our graph? It was an isochoric graph. Okay, so this one is isochoric. Now similarly in this, it's a horizontal line, which means pressure is remaining same, like pressure at this point is the same as pressure at this point is the same as pressure at this point. So when pressure was same, what we would say is it is an isobaric graph. So this one is isobaric. So these two graphs are done. Now usually in adiabatic and isothermal, you can't identify the graph just by looking at it. You need some more primitives. So here we can say that this is at temperature 1 and this is at temperature 2, and these two are at different temperatures, but this entire line, this is at temperature 1, and if I say this, so this entire green line, this is at some other temperature T2. And to compare T1 and T2 moving forward in module 2, we would be having other variables and other state primitives, which we would be helpful in defining whether T1 is greater or T2 is greater. For now it can be left as this, and the second PV graph as well. So it would be also yield a graph like this, adiabatic graph. But what we need to take into consideration is that Q would be 0. Then what's a cyclic process? If I am returning back to the same state, like let's say I have this state 1, which is by P1 and V1 over here, and state 2 which is defined by P2 and V2 over here. Why P1 V1 P2 V2? Because again, by considering the state postulate, we have two independent and intensive properties at both the states, so I can define these two. Let's say my system uses this path and goes from P1 V1 to P2 V2 and then uses this niche wala curve and goes back to P1 V1. Then I would say that this is a cyclic process because I am returning to the same state. Returning to same state. And so that's the cyclic postulate we have covered. Now we would be moving on to pressure. So this is an important topic. There may be some questions on this in your midsem as well. So we have four different kinds of pressure. But firstly, what exactly is pressure? Pressure is force upon area, and the normal unit that we use is Pascal, although we have other units as well. Other units like one is Pascal, which is simply Newton per meter squared. Then we have bar. What is bar? Bar is 10 to the power 5 Pascal. Then we say ATM. ATM is nothing but the atmospheric pressure, but we have defined one ATM as 101.3 kPa. All these, if it is an open book exam, you can write and take, it won't be an issue. Then we have torr, which is in mmHg. So like we say 1 ATM is equal to 760 mmHg. So these are different units, but mostly you would be using either Pascal or atmosphere. These two are important for us. Now absolute pressure. What is absolute pressure? Like if I have 0 over here, which is complete vacuum. So if I am measuring with respect to perfect vacuum or 0 pressure, 0 Pascal over here, then I am getting absolute pressure. So this value, the value of this arrow, would give me absolute pressure of P2. This arrow, this would give me the absolute pressure of P1. And then atmospheric pressure. Atmospheric pressure is the pressure that atmosphere is exerting on us. So like if I am standing, there is an air column above my body. So that air column, the pressure which that air column is exerting is nothing but the atmospheric pressure. So let's say we have the atmospheric pressure over here, and that is generally a good reference point to take. So taking the atmospheric pressure as the reference point, if my pressure is increasing, so if I am going from pressure atmosphere to a pressure which is higher than the atmospheric pressure, that's when I say that it is gauge pressure. So in real life you can take it in a counterintuitive way. Like if I am going underwater, the pressure above my head is increasing because now I am experiencing atmospheric pressure as well and the pressure of water above me as well. So the pressure increase, that pressure increase is the gauge pressure, and it is usually greater, so we represent it by positive. And the decrease, if let's say I am like climbing a mountain, so when I climb the mountain, the pressure on the mountain top, it is usually lighter, it is less dense, which is why the air pressure above me decreases. So that's when we say in a negative sense that it is a vacuum pressure. Now, and if they say, like if I am going under the water and they are asking me to calculate the vacuum pressure, then I have to like consider that P vacuum is negative of P gauge. So if they are telling me to calculate the vacuum pressure of when I am deep diving in the sea, that would be actually the negative of the gauge pressure which I calculate. And if in a similar way they are asking me to calculate the gauge pressure of when I am climbing on a mountain top, that would be the negative of the vacuum pressure which I calculate. So this formula would be very important if they try to trick you into calculating something which is not possible. You just put a negative sign and that would be it. Now then again we have seen that here P absolute is nothing but this arrow up to here and then this arrow, and this arrow we know is the gauge pressure and this is the atmospheric pressure. So that's how we get this formula that P absolute is P gauge plus P atmospheric. Now hydrostatic pressure, this is again very important when we see devices like manometers and things like that. So whenever we have to calculate hydrostatic pressure, let's say of a water column above me or any other liquid, we use this formula, which is P is equal to rho GH, where rho is the density and H is the height of the water column or the liquid column that is above me. So here let's do a question related to the pressure one. I'll just open it up. Yeah, so we are at the beach, which is sea level. So let's say like this is sea level, and which means I am at atmospheric pressure, which is usually as 1025 millibar, or I can write it in pascals as well. Then case 1 is given as A part is 15 meter down in the ocean. So we need to calculate absolute as well as gauge or vacuum pressure, and the second case is given as B part 250 meter elevation. So in this case also we have to both cases absolute and gauge or vacuum pressure. So first we can identify that this will yield my gauge pressure and this will yield my vacuum pressure. So let's try solving this question. Anybody can give me hints on what my first step should be?
So you should first
Be a little more
check the
interactive,
gauge
guys.
pressure. I mean, the change in pressure in the first two
Okay, hi
instances.
Sam, are you speaking anything? I'm unable to hear. Just a second. Is everybody else able to hear Sam? Just react with a thumbs up or something. Okay, wait.
Yes, sir.
Hi, can anybody speak up right now? Hello, yeah, can anybody try speaking? Hi, guys.
So you're audible. We can hear you.
Okay, still I'm unable to hear.
Well, also, I couldn't hear you. Well, so you would first check the change in pressure itself, which is delta P is equal to rho GH. And so gauge pressure, you'd add that to the atmospheric pressure to get the absolute pressure. I have one small question. I was wondering if you could send these notes somewhere, like. All right, cool. Thank you.